Okay, so for it to cycle through a table full of values, so we're going to go ahead and save as. Let's run this. See if it actually works. Oh my gosh. Oh my goodness. Holy shit. Today, we're going beyond PWM for our STM32 microcontroller, and we're giving it memory. Not internal memory, external memory. We're giving it an SD card. And you're gonna understand how they communicate with each other and why this is the gateway to proper engineering projects. It's just gonna unlock so many more opportunities. The goal for this is to store music samples. However, in this video, I'm going to show you how we read and write from the card. So stay tuned, don't go anywhere. First step, pick up an SD card module. I got mine from Adafruit. Make sure it's SPI compatible, 3.3 volt logic. This says 3 volt, but it still works fine. This is exactly how you want to hook it up. You can just use jumper wires, female to female, and I'm going to list the pins above. Okay, so we're going to open Cube MX, select your chip, and now let's go to connectivity, and we're going to go to Serial Peripheral Interface 1. Okay, and you're going to enable full duplex master. This is going to allow us to send and receive at the same time. Okay, now under configurations, select 8 bits, most significant bit first, prescaler 256, low 1 edge. You're going to disable NSSP mode. We don't need that for now, and leave the edge, leave the rest the way it is. Okay, now you're going to see that it enabled some pins over here. So it enabled the source clock and enabled MOSI and MISO. Okay, that is master out, slave in, and master in, slave out. Your master is your STM32 and your slave is your SD card. To make it a bit easier, I'm gonna set PA5 to the source clock. Okay, and we need our chip select pin. So we're gonna allocate, you can allocate any pin, but again, making it easier, I'm going to select PA4 because they're right next to each other. We're gonna set this to the output, and we're going to name this CS SD, just to make it easier. Now, this is chip select. So what chip select is that it's like almost like a push to talk sort of function. So, and it's weird because when it's high, it's not listening to anything, but you pull it low to let the chip know that you want to talk. So we have to set this because currently it's set to low. So go to system core, go to GPIO, and then go to PA4, and you can see GPIO output level low. So just go and set that to high, and that's all you need to do. Okay, and then come back. It's looking good so far. Now we can enable our FATFS. Basically, this is pretty cool. So go to FATFS and select user defined, which is pretty much all we need to do. What FATFS is basically a middleman. So the SD card is basically like a massive warehouse full of values in like a grid, and they all have addresses. So when we say, hey, listen, I want text, I want test.txt file, right? The SD card doesn't know what's going on. So the FATFS is almost like our translator. So we tell FATFS, hey, I want this file, and it goes and talks to the SD card and say, hey, listen, I need sector 1000 to 2033, right? And it knows where our file is to extract it, because we can't talk in, the hardware layer. We need to, so FATFS is basically a higher level program that organizes file. It's going to organize our read, our write, our files like that, okay? Okay, so once we've double checked and triple checked, we can go ahead and generate the code. So we click generate code. Oh, whoa. All right, this is where you don't want to screw up. Name the function, and then, wow, change EWARM to STM32 Cube IDE. That has got me too many times that it should have. okay? And then you can go ahead, make sure your project location is good, and now generate the code. All right, I'll see you when it's done, and then we open it in the IDE. Okay, here's the exciting part now. Let's open external storage project in the IDE, and you're going to want to open the FATFS file, okay? You're going to see fatfs.c, fatfs.h, and then look for user disk IOC and .h as well. They should all four files be there. Now, FATFS is the file system, okay, and it will call upon user disk IO as a lower level system to read, write, and initialize and all that sort of stuff, the disks. Now, because we've selected user defined earlier, we are going to have to make our own driver to put into user disk io.c. So if you come into user disk, if you open user disk IO, we're going to see, you should see this section here, okay? So user initialize, status, read, write, and the IOC can do the commands. Now, come down here and you see that user initialize, okay, it's got this code in here. We're going to have to replace it with a call function to our driver for all of these. So user initialize, user status, user read, they're all gonna, so we're gonna replace the bodies of those to go to our driver. So this is almost gonna be like a middleman, and it's gonna, FATFS is gonna rely on the user disk IO, and then the user disk IO is gonna be like, go to the driver that we made, okay? So let's go ahead and we're gonna have to make two files, a header and a source for our driver, and then I'll see you then. Okay, so now we're gonna add the files for our driver. It's super important. So go to core, and then you're going to right click source, go to new, we're gonna create a new source file. And we're gonna name it FATFS _ SD.c. Okay, there we go. And then we're going to right click the ink, and then we're going to do header file, and then we're going to do the same thing. So FATFS _ SD.h. Finish. Okay, now that's finished. Okay, so now we have the header file open, this header file, FATFS _ SD open. Let's go ahead and include these functions right here. Now, what this is going to do is user disk IO is going to call to fatfs.sd, the main source file driver. And then that driver, our main driver, is going to use functions in the header file. So from fatfs _ SD. Functions like initialize, status, read, write, and the IOCTL, okay? So now, what we have to do is we have to link our user disk io.c to fatfs _ so we have to link this file to this file, okay? So now let's open our user disk io.c, okay? And you can see it should have include. So where is it? Okay, so we got include. So this one here, we're going to add one that says we have to include our this one here. So FATFS _ SD.c. All right. No, .h. .h. Is that right? FATFS _ SD.h. Always got to double check with these things. Now we're going to, yeah, that's right, because it needs those. Yes, that makes sense now. Okay, now go down to the function bodies. So this right here, and then do return. So we're going to add the initialize function. Then we're going to go down to the user function, user status. So we're going to do the return to the SD disk status function. Now all these functions are coming from this main file here, this one. And then, so let's just keep going. The next one will be user read, return. Okay. So this one there, and then user writes. All right, so once you have all these functions inserted into the main body, now we can go ahead and get the main driver ready. Now let's include the driver. So go into your FATFS underscore SD.c. It's a mouthful of time, but you know what I mean. Delete whatever's in there, and then copy and paste your driver. This I'll include in the description. Don't worry, it is too hard to write by hand. You know. So I had to get this off the AI gods. So yeah. Now there was a couple of things missing from this. So what was missing? So we have to define this command, which wasn't defined. And then we have to scroll down to find the bytes. And whatever that is. And add CMD. Because apparently wasn't in there. CMD. All right. Now here's the nervous part. Now we have to hit build and see if this driver works. So go up to the hammer. I haven't got my SD card connected, by the way. Go up to the hammer. Hit build. Oh wow. Oh, what the hell? Okay. Alright, so we've ran into some errors. Let's sort them out one by one. Okay, so it's saying SD CS pin undeclared. And that's SD CS pin undeclared. So let's go to, because this includes FATFS SD, which SDH, which is this one, and then this includes our main H file folder. So if we go to our main H, then it's got everything here, right? So our CS, so what's it saying? SD, where's SD? Maybe, so maybe it's got it wrong. So, so look what it says. So our code was wrong. So it says SD CS pin, but on this one it's just reversed. So if we just change it to CS underscore SD pin, that should work. So that's what we're going to do. Yeah, I'm going to change this one. So instead of, this is going to be SDCS. So SDCS. It's actually pretty cool, I'm not going to lie. The fact that I'd have no clue what these fucking errors meant before, but now, man, I'm feeling like a whiz. So now it's saying SDCS GPIO port. So there we go, it's reversed again. So let's do SD CS. So this is the same error. I think we're good. Let's try run it again and see if it fails. I'm assuming it's not going to fail. Ready? Where is it? This one here? Come here, you sucker. All right. Build. Oh! What happened? GPIO port. Is that another one? It's annoying because it's a naming convention. It's not a serious error, it's just naming. But I fixed it here. However, the error is in main C. So let's open main C here. But this needs to get changed to SD CS pin. And then this one needs to get changed to SD underscore CS. All right, let's save it and try and run our thing again. Let's try and build it. What the hell? Another one? Here, oh my goodness. We're getting screwed everywhere with this damn naming convention. Lucky it's an easy fix. That's what I'm gonna say. Lucky it's an easy fix. SD. Anywhere else? Looks like that's it. Oh, all right. 0 errors. That is good stuff. So now once that works, let's jump over into our main C file. And then you're going to want to scroll down to user code begin 2 and paste this in. I'll put this down below as well. But basically what we're doing here is it's saying, so we're giving it a safety delay. And then Frez is checking if the mount was successful. And if it is successful, then it carries on. So, then it creates a file called test.txt and it writes a message into it. So this says create the file and this allows us to write into it. Then it checks again if that worked, if it's able to write. And then we start to tell it what we want to write, which is this. Apparently this RN is meant to close the sentence and make it look nice on the computer. Then we tell it the location of the file. We tell it what we want to write. This tells it how many characters. And then another, this is, I'm pretty sure the AND symbol represents like a file location. And then after it does this, we need to close the file. So it closes the file, or does it read? Okay, so it's going to read. It's got a read buffer. So then we open the file to read it. And then if that works, then it goes on to another one. So this code proves if reading and writing works. Then it goes on to close the file. And I believe if it's closed and everything's good, it will give us a solid green LED on pin LD3. Okay. Now, I will link this code. And also, before you do any of that, go up to the top and make sure you have these, you include these files and that you have these variables as well. If you don't have them, you will get errors. And then implement this code. So now we're going to build. Let's see if it works. Okay, let's do it again, hold on. Okay, so build finished, 0 errors, 0 warnings, which is good. Now we're going to finally plug in the STM, and then we're going to write this, and I'm going to show you what happens. Okay, so before we plug the SD card in, what I'm going to do is just show you that there is nothing in the drive. So it's completely empty. As you can see, USB drive. I'm just going to eject. Okay. All right. Now we pop this in. Again, this is formatted in FAT32, not FATFS. So pop that in there. All right. Just in there like that. Oh my gosh, sorry. And now get your data cable. It has to be advertised as data cable. And then plug it in. Okay. Should come up as a USB device on your computer. And as you can see, this is what we got so far. And I'm going to run it while we have this. And going to run it now. You're going to see that green light goes away. Waiting for the debugger. Downloading progress. Shutting down. Where's that green light? This happened before because when I tried the screen record, it downloaded something else and something weird happened. I'll try it one more time. There we go, it's back on. I don't know why that happens. But that means that we successfully read and writ. Oh my gosh, my English. We can write and read to the SD card. So that is a good sign. Now we can actually make a table of values and see if we can extract some files from it. So that should be exciting. Oh, let me show you that it worked. So let's actually take this out. You can actually take it out because it closed the function. With the computer, you have to eject because it might be doing some stuff in the background that you're not sure about. So ejecting just helps you know that you've closed the actual operation. With this, we know we've closed it. Oh, and there we go. It comes up. And if we click it, oh, hello from STM32 over SPI SD card. How good is that? Thumbs up for that. So we could end it right there, but I want to take it a bit further because this project requires me to put a table of values onto the SD card and then for the microcontroller to read those values and directly set the duty cycle. Now, the problem is that the values that are on the SD card in the file are characters, and we need to convert those to integers to directly set the duty cycle. And also, I didn't set another GPIO pin to test this theory. I'm going to open the file from within the IDE. So now that we're in, all I want to do is add another GPIO pin on timer 1. So PA8, timer 1, channel 1. Go to the timers, timer 1, clock source, internal clock, channel 1, PWM generation, and then we're going to set the counter period, the auto reload register, to 799. And then we're going to set the pulse to, I don't know, 800 to 400. Then we go to generate code. That's all we click. So let's click generate code. Yep. Code is successfully generated. All right, let's close this. Let's close this. And let's looking in the wrong area. I was looking under GPIO, but we didn't initialize pin P88 for GPIO. We initialized it to be a timer, and that's what it's done here. It's initialized timer 1. As you can see here, where is it? Here. MX time 1 initialized. And you can see 799 and our pulse of 400. All right, so now we're going to get rid of, just for a test, we are going to get rid of this code inside here and then add this code here. So we're going to set our delay again, and we're going to start timer 1, channel 1, and then we're going to convert 500. Actually, it should, we're at 50% duty cycle now. We should go to like 600. 600, so we should get near full duty cycle. Should do 650, yeah. And then, so that's going to write it 650 in characters, and then this ATOI function is going to convert that into an integer, and then it's going to set the duty directly. All right, so we should see, so right now I'll plug it in and I will show you the duty cycle on the scope, and then I will upload this and then I'll show you the duty cycle on the scope. Yeah, so this is nothing to do with the SD card just yet. It's just to show that we can actually convert these values, and then yeah, so we can grab the values from the SD card, convert it into an integer, and then set our duty cycle, which seems like it does a lot of programming that quick. Like, this thing's got a sample at 44.1 kilohertz, and it's going to be doing this like 44,000 times in a second. That's insane. It's gonna, what? I don't even get that. All right. Okay, so we uploaded the code to the microcontroller, and then that looks roughly about nearly full duty cycle. That looks about, 80%. So that is good. Now what we're going to do is we're going to make it actually read the value from the card. So that test text that you see 650, we're going to actually read that from the card. So we're actually going to have to make a file with 650 in there and let it read that file and then set the duty cycle. Let's now create the file of the duty cycle so it can read, so the microcontroller can read from the SD card. So go ahead and delete what we already have in user code begin 2. Paste this in. What this is going to do is read from this duty text file that we have to create, and then convert it to an integer, and then set the duty. So open notes. I'm going to open notes and then create 650, a file called 650, save it as, now I have the SD card in here, so save it to here, 650.txt, and then I'm going to make another one where it's like 100, right? Save that as duty 1. That way we only need to change that name to 1. Let's save it there. Oh, wait a minute. Hold on. No, that's wrong. That needs to be renamed. Duty. There we go. All right, so duty 1 has the value of 100, so we should see small. All right, let's go back. All right, so now that's in the card. Now we could probably flash it. We'll flash it with duty 1 on there actually. And so let's eject the card now. Eject. All right, take the card out. And then put it into our module. All right. Now, let's plug this in. I want to show you because I've got it up to the oscilloscope already. Let's flash. All right. Let's go ahead and flash this. Oh. Wait a minute. All right, so we're going to hit run as application and you're going to see, yes, click OK. All right, it's going to start running. 0 errors. Waiting for the debugger. It says shutting down, build finished. You know what? It's really frustrating with this, anticlimactic. Normally it wants me to do it twice. I don't know why. Oh, okay, here we go. Waiting for debugger. Downloading progress. There we go. I don't know why it acts like that. But look at that. You can see the 100% duty cycle, like 10% duty cycle, or less than 10% actually. That represents 100. And then if we change one thing on the file, so if we go to here and delete that, that's 650 now. So if we go ahead and run as, click OK, right, I want to see that change. Yeah, we might actually have to do it twice because it's finished, so let's go ahead and do it twice. Okay, let's have a look. Excuse all the mess on the desk, sorry. All right. And it actually looks the same. Oh wait, no. No, that's, sorry. My bad, the cursor's in the way. Oh shit, sorry. The cursor's in the way because that is, let me move that cursor out of the way. That's controlling the voltage. Yeah, that's full duty cycle right there. That's a 650 duty cycle. All right. Okay, so for it to cycle through a table full of values, what we're going to need is the while one loop now. So that's the loop that keeps repeating itself. So we're going to store this code in here. This is pretty much the same code. However, now it says, so yeah, we're going to open it. The same sort of stuff, you know, convert it to a duty cycle, to an integer. This one here, so we have a duty of 0 to 799, so we can go ahead and just fix that up to 799. And then we're going to have a hold delay of 100, and then hold delay 500 after you close the file. All right, now our file name is not going to be duty, it's going to be table.txt, and we're going to make that, I've made the table here. I've almost like mapped a waveform that I want to see. So, you know, it's sort of, you know, low to jumps really high, and then as you can see, it like gradually goes lower and jumps really high. So I want to see like an abnormal pattern that I created just to know that this table's working. So we're going to go ahead and save as table text file, and then we're going to go into our USB, delete these two just because I do not want them anymore. We've got table. All right, now should we go ahead and eject this disk? Eject. All right. Oh. Go ahead and put that SD card back in. And if everything is meant to be, and if we, write the code twice, okay, we've got that up there, running the old code. Again, I want you to still put your variables and this in user code begin to. And yeah, let's go for it. And see. Saying not applicable. What about I just hit play? All right. 0 warnings. That's good, so it built correctly. Oh. Okay, so the problem was that I didn't have another curly bracket right there. Let's run this. See if it actually works. Oh my gosh. Oh my goodness. Holy shit. Look at it. Look at it following. That's following the curve. The random. Oh my gosh. Oh my gosh. And there we have it. We've just proved that we can read a table from the secure digital card over the Serial Peripheral Interface protocol, which is crazy. So we've just connected external storage to the STM32 successfully. Now for this project, I had to rely heavily on the AI gods. Honestly, how fast you learn, iterate, and troubleshoot with artificial intelligence is just unreal. Like, if you just don't use it, you're gonna fall behind. The person that's using it is gonna win, and if you don't use it, you're gonna fall behind. So I think that's just modern engineering. Now, the other thing is this video also proved how important learning communication in engineering actually is. It's the only way we can communicate, we can use computers. Think about it, through keyboards, mouse, displays, getting sensor information, like a camera. Looking at a camera, the sensor sends information to the screen, right? Now, that's the same thing with external storage. So this unlocks just more serious engineering projects that we can achieve. If we understand SPI communication protocol is just one of many communication protocols. So I'm looking forward to learning some more in future videos. And I genuinely hope that you learned something from this video. And if you did, thumbs up. If you didn't, if you ran into some troubles, I would suggest lean on the AI gods as well, okay? It's so good at debugging code and just teaching you how it all works and how all the layers come together. It's unmatched. So look, as always, thank you for watching, and I'll see you in the next video where we make this play music once and for all. Once and for all, this half drive is gonna play music. All right, see you guys.